Calculus lesson, how derivatives affect the shape of a graph. We have a warm up. Try to do this on your own and see how it goes. Okay, guys? This will sort of warm you up into this topic. All right, let's get started. Okay. Actually, in this particular case, I think it's kind of good to know how to do this. Uh, this is nothing really new here, guys. So this is what you should have gotten. And even before I began, you remember I always constantly tell you guys, don't forget what we learned in the past, right? Even though we are supposed to use the new techniques over here, we know that it's positive cubic looks something like this, right? Or like this. It depends, right? But we know that it's from the left to right, it's going up and down this way because it's cubic. There are up to three real roots, right? And so when you do the derivative and did all that, you find that there are two relative extremas, and then it's positive slope, negative slope, positive slope, exactly what we expected. Plug in the values to find if you get the negative values, the y values associated with that, and then what I did, okay, and that was it. And then over here, when is it increasing? When the slope is positive or negative, right? If it's positive, it's increasing. Slope is negative, it's decreasing. I just stated that as it is. You looking at this number line, and then I just graphed it, right? All right, guys. In this particular question, this might have been a little bit more tricky. For what intervals is the rate of change of f of x increasing? Wait a minute. So when is the change increasing? So, for something to be increasing or decreasing, we have to be looking at the slope. So we'll look at the slope of the change, which is the second derivative, right? And when you look at that, guys, we know that when x equal to 0, f double prime is 0, to the right is positive, and to the left is negative, right? So it's increasing when x is greater than 0, it's decreasing when x is less than 0. All right, guys, here we go. So we have a theorem, guys. So we have an increasing, decreasing test, and well, just like what we talked about, if the derivative is positive, the function is increasing on that interval. If it's negative, if it's decreasing in the interval, right, guys? So how do I graph this? Okay, where is it increasing and where is it decreasing? Interesting. All right. Once again, even before I begin to answer this question, I look at the fact that this is the fourth. It's a positive fourth. So it's going this way, and there are up to four real roots. So what that means is that it could look like this. 1, 2, 3, 4. It's just that depending on the values that follow it, it could look like this, or it could look like this, right? Or it may only have three answers. 1, 2, 3. It has up to four. Okay. Hi guys. So let's, using this information, let's get it done. So we're gonna take the derivative, which we did here, guys. And I took the derivative and I factored. And f prime is equal to 0 when x is equal to negative 1, 0, 2. Plugged it in. And that's cubic here, isn't it? And cubic looks like this, doesn't it? So 1, 2, 3. And then this is negative, positive, negative, positive. Or you just actually plug in the values over here, or do sign analysis to figure out what the f prime values are. So if it's positive, it's increasing. So f is increasing over, and x is in, or a negative 1 to 0, or 2 to infinity. And the function is decreasing when x is from negative infinity to 1, or 0 to 2. Looks good? All right. And then we learned that this is how we find local extreme values, right? And suppose that the c is a critical number of the continuous function, and if the f prime changes from positive to negative, like this, then to this, right there, at that point, it's a local maximum if it increases and decreases. Hold on a second. So increases and decreases. So local maximum occurs here. Nice. But we kind of knew that, didn't we? right? Because that's going to be like this, right? Or something like that. Yeah. Anyways, and then when f prime is goes from negative to positive, so slope goes down, then up. So at that point, it is a local minimum. So when f is positive left to right of C or negative from left to right of C, then there is no local maximum at C, right? In other words, um, if it's like a positive and positive, at that point, there is no, um, yeah. What looks like that, guys? Can you imagine? I think what this might be talking about is uh, positive to the left and the right of C. So if x equal to C here, slope is like this and like this. And yet slope is 0 here. So I think we're talking about this kind of shape right here, right? If it's negative at x equal to C right there, and it's going down this way, it could do that by doing this, right? Right. I think this is called an inflection point, but we'll talk about that later. Okay. So from this information, what can I do over here? So I already talked about one of them, didn't I? All right. So looking at this is what I have. So this thing over here is going down, goes to 0, then becomes positive. And here it goes up, then 0, then negative. And this thing is 0, and it goes up again, right? So it has the shape that we kind of predicted, right? To figure out where exactly these values are, I'm going to have to plug it into the f. But even without this, right, I know that local minimum occurs when x equal to -1 or 2, and local maximum occurs when x equal to 0. However, this is not what they're asking for. They're asking for what is the maximum or minimum value. When they ask for that, they're referring to the y value. Okay, so for that reason, I have to plug it in to -1 into the function, and that's exactly what I did. I get -4, 1, and -31. I don't know if you noticed what I did over here, guys. Look, I just factored x squared out here. See this right here? If I both put 2 in there, instead of having to deal with 2 to the fourth, the number could get pretty big real fast, right? So that's a 4 right there. And when I plug it in, that's a 12. -8 minus 12. These two cancel. So 4 times -8 is -32, plus 1 is -31. For me, I like to manipulate the expressions so that I don't have to deal with the big numbers, all right? Yeah, that's just the way I like to do things. And I try to avoid using calculator because I find that I get too lazy with my brain, right? But anyways, so now that I found all these values, right, this is how you say it. We could say that local maximum is 1 at x equal to 0. Well, you could say it that way. But a more succinct way of saying it, more compact way of saying that, is the local minimum is at, so minimum, local minimum is a y value, remember that. So you have to stick the y value. So y is -4. And where does that happen? When x is -1. So this is a more compact way of saying it. So instead, over here, what I could have said is instead of that, f of 1 equal to 0. No, f of 0 is equal to 1. Let's try it again. F of 0 is equal to 1. Okay? All right, guys. And then over here is obviously f of 2 is -31, meaning this is -31 happens at 2. So if I take this into consideration, this graph should look somewhat like this. -31 is over here, and the -4, let's say, is, oh, I don't know, here, and 1 is like over here. So it may look something like this, except that this thing should go down much further down, right? I don't have space for that. All right, guys. So that's that. The next page. Uh, graph of f lies. This is an interesting way of defining what's concave up or down, right? Every book does it a little bit differently, but this is quite interesting. If the function graph of the f lies all above the tangent and the interval, then it is called concave up. Hmm. So what that means is that, CU means concave up. So if I were to draw, let's say, a tangent line, see that right here, guys? Yeah, it's curves up, right? If I draw this, curve is up. And if I draw over here, this curve is higher than the tangent line, right? Right. And then if the graph of f falls below the tangent on its interval, it's called concave down, right? So if I drew it over here, all these points are below that. So it's concave down, right? Yeah, I mean, that's a good way of thinking about that. So instead of straight line, it curves downward from the tangent. Or if it curves up from the tangent, curves up, concavity up, right? So that's a good way to remember it. Okay. Anyways, so when you look at that, that part right there, there's like a dome shape is concave down. See that right there? Concave down and concave down right there. It's going down, right? If it's a part of the U shape or parabolic shape like this, or like this, it's concave up. Okay. Whatever works for you. Okay. Concavity test. And the way we do that using calculus is that I take the second derivative, which if it's positive in that interval, then we call that concave up. If the f double prime is negative for that interval is called concave downward on that interval. Yeah. Okay. So let's take a look at this right here, guys. In figure 8, um, shows a population graph of the Cyprian honeybees raised, right? Uh, let's see. How does the rate of the population increase change over time? Blah, 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 blah. Concave up, concave down. Okay. So we could tell that, let me choose something other than, let me go green here. That right there. So it's concave up here. And from here to here is concave down, isn't it? So the thing about concave up is that initially my slope may be like this, but my slope increases over time. So here it looks like this, and here it goes like this, and it stops increasing. It starts decreasing again. That's where the concavity down is going, is that my slope is decreasing. From here to here, it's decreasing. It's up because from here to here, it's increasing. The point at which it stops increasing is the inflection point. And the funny thing is, that's when the slope is the highest. Therefore, it is the highest rate, right? So the highest point occurs at inflection point, right? So that question occurs, I think, let's say around 12 at x equal to 12. Okay. Concave up here, that is from, I'm going to say it's that's here, right? From 0 to 12, and concave down from 12 on, 12 to positive infinity, right? All right, how does the rate of the population increase, the rate of the population increase change over time? So basically, it's the slope is increasing, the population increasing at a faster rate. So the way I would describe it is that the population, okay, is increasing at a faster rate from, because that's basically what concave up is, right? From t equal to 0 till t is equal to 12. And then I think in econ, this is called point of diminishing return, where it stops increasing and the increasing like gets smaller, right? It's still growing, but it's increasing at a slower pace, right? And then starting at t equal to 12, the population is increasing at a slower rate, right? So it's like it's think of it as a position, right? If this is a position of a car, you're still going forward, but you're so slowing down. That's what that means, right? So this is a slowdown. Yeah? At a slower rate, basically means it's slowing down. Okay, that's it. All right, guys. Okay, so let's move on to the next one. So looking at this, how would I graph this, right? Sorry, and the inflection point right here, guys. Um, the point P on the curve is called inflection point. Point P, so that's a coordinate. So if I just say what's an inflection point, give me a coordinate point. But when does a inflection happen for what x value, then you could just give me x value, right? If f is continuous there and the curve changes from concave up to down or down to up. Remember this, guys. Inflection happens when the direction of concavity changes. Sorry, it's getting really messy. Changes. That's important. Not when it's equal to 0, right? So it may change over the fact that f double prime is equal to 0 or is undefined. Okay. So question is, how could you graph this right here, guys? Can you give it a shot? All right. This is what I have. So first thing I noticed was that is positive. Everywhere except this vertical asymptote. So there's an asymptote over here, just going up this way. So I know it's just going up. I don't know how, but it's going up. And this is positive, meaning it's like U shape. But then again, it can't go down, so it has to go this shape. When does that happen? When x equals less than 3 or greater than 3. Just like this, right? But there's an asymptote over here. But it's negative from 1 to 3, from here to here. Oopsie, I forgot to write it down. And that's 1, right? So because it's concave down, it's going to be like this. Because this is not, because we're assuming this is a continuous unless otherwise indicated. So it's connected. So it has to look like this. So that's the best picture that I could come up with. Right? But it doesn't tell you where it starts. Right? So I could have had this image like this. And I could have had this like, oopsie. Hold on, let me just grab it this way. Like this or this. But it's easier to show where that is. So this is what I drew. Okay. All right, guys. Why don't you guys go ahead? Well, let's talk about the second derivative test. If f double prime is continuous near C, right? We say that if the derivative is equal to 0 and the concavity is positive, it's local minimum. Whoa, whoa, whoa. Let's think about that for a second. So if its concavity is positive, it's a U shape. So this one is when it's a U shape like this, and slope is equal to 0 at that point. Yep, it's definitely local minimum. And this concavity down, isn't it? So it's like a mound, it's a frown actually, right? And then slope is 0 at that point. Yeah, that is local maximum. So you could kind of see, right? Because this is negative because slope went from positive to negative. It's decreasing like this. What goes up comes down. And this is positive because slope went from negative to positive. So it's increasing. So it makes sense. What went down must came up. So therefore, I must have gone through the minimum value. I must have the low point. Did that make sense? All right, guys. All right. So why don't you guys go ahead and try this problem right here. But before I begin, I mentioned this too many times. Don't forget the techniques that we had learned from the past. This is the fourth power, which means that it goes up in the either side, and it may have up to one, two, three, 4 points. It doesn't have to, up to four, or it could be like this, right? 1, 2, 3 points. So yeah, just be careful. So you know that initially it's going to go down, towards the end it's going to go up, in the middle it'll go up and down. It depends, right? All right, guys, give it a shot. What I got for this one was this. I took I set equal to 0 first, and I know that the x intercept is 0 and 4, right? Yeah, 0, 4. And then I took the y prime, which gave me this. So when I set that equal to 0, my slope is equal to 0 when x equal to 0, 3. I drew the number line for that. So it was negative, negative, and positive. Hmm. So my slope is what? My slope is negative. Oopsie, sorry. My slope is negative. It's more negative. It goes up again. Right. So when the sign changes, there's a maximum or a minimum. So this is the minimum happens over here, right? And then what else is true? Use this information to sketch. Okay. What I like to do is I also take the y double prime, and then set that equal to 0, right? The 0 happens when it's 0 and 2, right? And the signs change. Okay, so this thing looks like this. It's upside down. It goes up again like this. So we got to put all that information together. So I'm going to put all that information into the graph that I just drew, right? So I know that for a fact that my x-intercept is a 0 and 1, 2, 3, 4. 4 should be here actually. So what that means is that curve right there should be even faster. So that's a 4 right there. Right, so that would be 4, 0. That would be 0, 0. And this point right there is, what is it? 3, negative 27. And this right here, and that is neg 2, negative 16, right? So let's do this to discuss the concavity, right? So concave, using this information right here, guys, is concave up where? Negative infinity to 0 and 2 to infinity, right? Concave down from 0 to 2. Okay, check. And point of inflection occurs at 2, negative 16. Check. Local maxima. Local, there's no, see, there's no local max. In order for it to have a max, my slope has to go up and come down, right? Positive to negative, didn't happen. So local max is none. What's and then I gotta figure out my local minima is local min is minima or maximum is plural, right? There could be more than one. In this particular case, we only have one. Is f of 3 is negative 27. So local minimum value is negative 27, which occurs at x equal to 3. All right, guys? Okay. I suppose that is it. And let me move that picture slightly further up. See? There you go. All right. And perhaps I should move this up a tiny bit up. This way, maybe. That's all right. This is good. Okay. This is long. This is pretty long, isn't it? All right. Sorry about that, guys. We have one more. Um, why don't you try this on your own? Right? Try this on your own. At the very end, use decimals, and you should probably use your TI as well, right? Just to double check your work. Okie dokie, guys. We'll go over this in class. Okay. All right, guys. But do try this on your own first. All right. Have a good night.